So I'm going to conduct a series of session where I'll be talking about different image video AI models which are open sourced, and we'll be also discussing some closed source model. So in today's paper reading session, we are going to look at Sana, which is an image and video model by NVIDIA. So first, what are diffusion models? So a lot of you guys must be knowing what are diffusion models. So this is just an overview. So basically, image and video models work on diffusion model. It's basically a type of neural network that learns to add noise to a picture, which you can see here, and then learn to reverse the process. So adding noise is called forward diffusion, and then reconstructing image by removing noise is called reverse denoising process or reverse diffusion. So let's understand it in detail with an example. For example, we have a lot of training data of sprite images, and we want to generate more images of sprite. So first thing what we need to do is we need to make this neural network learn about what sprite is. So how will we do that? So there are fine details which we can make model learn. For example, the color of the sprite, the outline, the shape, or everything in between. We can do this by adding different level of noise to these images. Now the neural network is trained and learn how to mm, how to add noise to the sprite images. Now the model is trained, and uh, there is okay. So we get a fully noise image. As you can see here, a little bit of noise is added to Bob. Then here we can see a bit outline, more noise is added, and finally we get an image where fully by noise where we can't see anything. So now this image, this process is the last image which you can see is the reverse diffusion. So this image is taken which has fully noise, and then it is denoise. Here you can see a person, then a little bit of noise is removed. We are unclear with which person is this, or it is Bob or Fred sprite, and then again more noise is removed and we get Fred. So this is generally denoising. Next is okay. So now what actually goes on? Here I'll explain sampling. So this is after you have trained the model by adding noise. So this is the reverse diffusion where we take this image, which is a fully noise generated image. Then we pass it to trained NNN, and then we get a predicted noise image by that model. Now what we do is take this predicted noise and the original noise and get another image. So basically sampling algorithm uses DDP, which is denoising diffusion probabilistic model. So it is subtracting predicted noise from the predicted noise from the original noise. So here is the formula for it. Now the architecture, it uses CNN unit. So the input of the input image, which is given to a model, the dimension and the size remains the same. And when it comes out, its dimensional and size also remains the same. So here in input, the image is downsampled. It is downsampled and passed to a hidden layer. So when it is downsampled, none of the information is lost. The hidden layer contains all the information, and then it is upsampled and we get the original size, image with original size and dimension. So this upsampled is a little bit explained in detail here. In third diagram, you can see embeddings. So while upsampling, there are two embeddings which we can do. So first is the context embedding. So in context embedding, it helps you to control what can model generate. For example, you can give it a prompt like bird flying, or maybe generate Fred or generate Bob. So by giving a text description, it gets an idea of what to generate. And this context embedding is multiplied, whereas the time embedding is added. Now, what is time embedding? It tells the model what the timestamp is and what kind of noise level we need. So there are different timestamps, T1, T2, T3 uh, of the images. So the time embedding tells the model which timestamp we are on and what level of noise each timestamp needs. So how are this diffusion models trained? So this is the algorithm. You can see sample training image, sample timestamp, then sample the noise, then add noise to an image, then input it into a neural network, then compute the loss, which we see here, and then back propagation and learn. So this is basically the training. So this is an image of a sprite plus a little bit of noise is added. Then it is passed to that trained NNN and it gives an image with noise. Now this image with noise plus the noise which is added, both are taken, the predicted image and the original noise which is added are subtracted and we guess the loss function. Now whatever the loss is, it is given back to an LLM and then recursively it is trained based on that. It is not only trained with one sprite but different sprites or different images to just get an idea. So basically it is trained because to so that the model understand what noise is and what noise is not. Next is controlling. So what there is something very special about embedding. So what's special about embedding is because they can capture the semantic meaning text with similar content, it will have a similar vector. For example, here it is given a ripped avocado. So it adds some noise to it. It trains and everything goes on similarly. Same for a comfy armchair. The embedding works. Now you can see here the vectors. Here the vectors of some words are same. So when you ask for avocado armchair, it already has the similar vector data semantic similarity, and then it's easy for that model to predict it. So it gives an image of avocado armchair. So this was all about image generation through diffusion models. Now I'll just give you an overview of how video is generated through diffusion models. So video is nothing but just the collection of images. Oh, one thing I forgot to tell you is this is also called this step where embeddings are added or where you give prompt to a model. It's called conditional diffusion. Uh, so next is video. How are videos generated through diffusion models? So videos are nothing but a collection of images. So first is when you give a prompt for a particular sentence, like a bird is flying, it generates different images. And this is T1. It's very similar to image diffusion. So different images are generated. So to train the model to do reverse diffusion, we can take all 4 images from a particular timestamp, that is T1, as a batch, and then input it to training data, add some noise and input it to training data. So next is, you can see here, the label is exact noise of the noise pattern that needs to be removed from the each image to get slightly less noisy image from the previous time step. The goal is to minimize the distance between the predicted noise and the actual noise. So next is, so this batch of images goes into the model and of corresponding noise to be removed, and this corresponding noise come out. Now in fourth image, we subtract the noise from the image and that get a slightly noisy image. Now we take the timestamp of the input image, which has noise plus the noise generated here, subtract it, and we get the original reconstructed denoised image. Okay. So this process of video diffusion, which is similar to image diffusion, has two main challenges. First is the temporal consistency. So when you give a prompt to a model, for example, per taking a flight, you can see your four images are generated, but they are not consistent. They are different from each other. The branch is different, the birds look different, and it doesn't align and doesn't make sense. So whenever something comes out of the video generation model, we don't just care about each image individually looking good, but it should also make sense. So a model always needs a way of understanding or how earlier frames looked, and what impact it had on each other in order to generate a consistent image. So basically, the problem of temporal consistency. Temporal consistency means motion movement. So that's what is one of the main challenge. So how it is solved. So these images which we saw before are just the collection of images. So these are individual images. So what we do is, since these are just collection of images, we can think of them as a 3D matrix or a 3D cube. And instead of passing in each image separately, which we did earlier, we can actually break this big cube into sequence of small cubes or patches, because these patches span across multiple images in the sequence. They are known as spatial temporal patches. So this strategy will enable us to get better temporal consistency. So now these patches are given to a diffusion model, which is a transformer vision model. So when we train the model, we pass it in batches of noisy space-time patches. And one of the best thing or the good thing about the transformer model is its attention mechanism to figure out for a particular patch which other patches are associated and relevant frame. So this is the first image, and if we take this third, it due to attention mechanism, it automatically detects what will be after or before the image. So that's another good help. So that's how consistency is maintained. The second main challenge is computational demand. For example, let's take 24 frame per second uh, into 8-second video. So for in order to generate this, we need 192 images. And if that 192 images are of 720 and 128 p, then its pixels will be approximate to 17 millions. That is too much. So we need to solve this. So in order to solve this problem, we have something called latent diffusion. Now, latent diffusion is used by a lot of open source companies like Stable Diffusion. So what is latent diffusion? So latent diffusion is a type of neural network that condenses image into the latent space. This is the latent space. and it contains of two components. First is the diffusion model, and second is the autoencoder. Now, this autoencoder has two components. First is encoder, and the second is decoder. So when an image is encoder takes the image, produce the compressed representation of that image, and encoding is done. And decoder takes that encoded image and is able to return the original image. Now think of encoder as a series of layer that gets smaller and smaller, compressing the image, and decoder as a layer that gets bigger and bigger, reconstructing the original image. Now the main thing here is encoding. It's smaller but retains all the critical information. So even if it is compressed, this has all the information, nothing is lost. So basically what is done here is, instead of applying diffusion on pixels, it is compressed and diffusion is applied on latent space so that it reduces computational cost. So now the training of diffusion model. So this is the 3D cube. It's broken into samples, and it's given to encoder. It compresses it and gives small cubes. Then noise is added to it, and we uh, get samples with noise added to it. Then in inference step, we get a dimension over latent space. This is the matrix split into patches, which goes through diffusion model. So this is this one, which is again broken, and it goes under diffusion model, iteratively denoising the patches. Then it passes through the decoder, and we get out of the latent space, and we get an image, or pixelated image. It's not in latent space anymore. Also, this was just an overview of how diffusion works in images and videos. This I will be discussing about Sana. So first we'll be discussing about the image. So Sana is a text-to-image framework that can effectively generate images up to 4096 and 4096 resolution. It can be run on local GPU, and this is the comparison of Sana with other big models like FluxDev SD3. Even if Sana is like 1.6B to 0.6B, it performs very well compared to this FluxDev and SD3. So FluxDev is basically, we are comparing this FluxDev of 12 billion parameters. So yes. So this is the algorithm and system optimized to make it better. We're talking about Sana, so this is basically Sana. So there are this is the FluxDev model of 12 billion parameters, and it has 1023 seconds. Sana baseline without any optimization has it takes 469 seconds. Then after adding deep compression autoencoders to Sana, it reduces to 41. Then after adding linear DIT, it reduces to 24. Then after adding kernel fusion, 21. And then DPM solver, it reduces to 9.6. So these four are the optimization layer which we will be adding to Sana in order to make it better. Let me explain this bit in detail here only. So the first layer, deep compression autoencoders, what it does, it is compresses the image. Uh, in it compresses the image. Okay. And in linear DT, what it does, it replaces the standard quadratic equation with linear equation. Uh, and in kernel function, what it does is it combines multiple GPU operation into one single GPU kernel instead of like launching them separately. And in DPM solver, what it does, it reduces the number of denoising steps. For example, it takes if something takes 20 steps, it will reduce it to 10 steps. So even though Sana is 2x smaller in parameter, it is 100 times faster. So very first optimization layer is deep compression auto encoder. So F here stands for spatial compression factor. This is the compression factor. So first, let's see first diagram. So input is given to SDVAE. Now, what is SDAV? It's similar. It's same as latent diffusion that we talked about, but it also has one layer where it adds where video models are trained and they are added separately. Sora did that, I think. Yeah, we'll see that later. So it has 8x. So for example, it is 1024 into 1024 image. It becomes, so it is 8, right? So it's divided by it. So 128 into 128 latent. So the tokens which are generated here is 16, let me calculate. 16384 tokens, and comparing DCAE model, which is auto depression compression, deep compression autoencoder. It has 32 and 64 F, so it's divided by 32 and 64. If 1024 is divided, we get only 256 tokens. So compared to this two, this has less number of tokens. So now there are three phases of training strategy which AE uses. So in first, low resolution full training, both encoder and decoder are trainable. So both are trainable. In second, encoder and decoder are frozen. Only the adapter, the latent adapter is trainable. Because its training is expensive and we are already trained the decoder encoder, there's no need of training it again. Only the adapter, which is the bottleneck, it learns to bridges the gap without retraining everything. So we don't need to retrain everything from scratch. Latent adapter training is enough. Then is phase 3, where encoder decoder is frozen and GAN loss is added on top of reconstruction loss. Now why GAN loss is added is there are three things. So first, in order to make something look real or not, because it GAN loss guesses tells if something is real or fake. Second is to make image look realistic and detailed. And third is sometimes it does generate blurs, so it fixes the blurs. So that's the reason GAN loss is added in phase 3 in raw resolution and local refinement. So next is the architecture of the SANA model. So you can see here a prompt is given to a model, a cyberpunk cat with the neon sign that says SANA. This is the CHI prompt generated. So a small LLM is used, that is JAMA. gamma decoder only, because it can understand the sign, the text written on this sign. So that's taken. Second is the time embedding. Now the model needs to know which step it's on. That's the reason time embedding is taken. But we don't need position embedding. Now, why is positional embedding removed? Because a standard transformer needs position embedding to know the token's order and location. So, but here the position embedding is removed. So how are we going to know the position and location? So that's where mix FFN comes to play. So in this architecture, we have mix FFN, which has 3 into 3 convolutional network, where it encodes the position through local spatial structure. So it just checks the neighbor and node. So that's the reason we don't need position embedding. So it's the first DIT without positional embedding. So it's a notable contribution here. Then encoder here. So yeah. So linear attention, mix FNF, cross attention, and this symbol here is of residual addition. Then let's talk about diagram B, which is the linear DIT model. So in this linear attention mechanism, N in, so there are two terms, N into D, which are tensors. Now N here stands for number of tokens and D stands for feature dimension. So first step is to create QKB. So these are the linear input, and the shape of this dimension are N into D. This is just the transpose, and of this, that is D into X, and this is N into D. So Q stands for query, what am I looking for? K stands for key, what do I contain? And V stands for value, what do I actually pass on? So then these are then ReLU is applied. It's an activation function, a nonlinear activation function. So this is applied, not softmax. Now here we can here they did not use softmax because it increases the computation. If you use softmax, you'll get n into n, the n square, and the drastically the cost of the model will also increase. So we are using your ReLU. Then it's given to mathmal function. And here, as D is small, we get D into D, which is a tiny matrix, and scaled. So the output is Q into K into V. So whatever the output we get is divided into square root of D to prevent the values from exploding. So whatever the cost is, it's linear in count, not quadratic for this linear attention. Next is mix FFN mechanism. So first is 1 into 1 convo layer, which combines the features across channels in sample position. Then we have 3 into 3 convo layer, which combines features from neighbor. As I said, it checks the neighboring position. Then we add ReLU, and this is basically the non-linear gate function, which is used in decision making. And then it's again passed to 1 into 1 convo layer, which restores the original dimension of the image. So about this gating mechanism, so as I said, it's a decision making. So one branch controls how much the other branch signal passes through this. So it's basically similar to LSTM gates, but they are much more simpler. And Avadilu, it's a activation function. Uh, so another problem which is in the paper is about the caption generation. So the training data for image generation needs good text caption. Now, original data set does not have a good caption. So what it does is, you can see here there are three processes. So what it does is it uses VLM. So it basically um, uses other models like ChatGPT, which can understand text very well, and then it asks that model to generate the caption. So first step is it feeds images to multiple VLMs, get multiple captions, then it computes the score of each caption, and whichever caption score is high, it during the training it picks up that caption and uses it. So the last optimization layer is DPM solver. Now it's basically related to flow URL needs plus flow matching. So there are two terms. So in this, it the main goal is to reduce the steps. So if something takes 50 steps in generation, it reduces to 42 12 step. It does not go in linear format, it directly jumps uh, from timestamps in order to get the same results. Mm, the performance versus speed. So there are different model like Flux. So these are better. This has high quality, but they are slow. Sana is probably best SOT model in this chart. So this is the direct 4K resolution image generated with perfect detail. And these are some visual comparison with other models. So even if the model is small, it's generating very good image. And the best part is you can run it locally. So that was all about Sana. Now it had like three iterations. So Sana, then Sana 1.5, and then there is Sprint. So uh, now we'll talk about Sana 1.5. It's not dependent, but it's similar, and it's very similar to Sana. Just there are two steps which are added here. That is prune plus VLM. So Sana 1 was fast and efficient, but then they asked like, can we make it much smarter and higher quality without paying full training cost? That's what is covered in this paper. So first is efficiency training, that is the model growth. So from Sana, the main Sana, 18 layers are taken, then one M layer is added, and that's how it's trained. And that's how the first model is. There is a 8-bit game optimizer which stores training states in 8-bit instead of like this one into 32-bit. So it's like 4x less GPU memory needed during this training, because already half of the data we have that's not changed. So we don't need much memory. Next is about prune to any size and depth puring. This is the model depth puring. So what it does it scores every transformer blocks here. How much does it affects the quality? How much does that block affects the quality if that block is removed? For example, if something is highly affected, then it and has high score, then that block is kept, and block which has a low score and does not affect or has a very less effect is removed. So that's how only the needed blocks are kept, and that's how the model can be shrunk into cloud GPU or mobile version. So and another thing is that as the blocks become less, there is we can only like retrain just that 100 steps on one GPU. So the quality is also fully restored. And the third you can see here is it picks the best output from the inference scaling. So it generates n candidates images for sample prompt, and then it uses a VLM to judge which image is best. So there's a tournament badge, and the winner of that tournament badge is the best image, and that image is kept, and other images are thrown. So this alone pushes the Gen eval from 0.81 to 0.96. So this is all about Sana 1.5. Now, Sana Sprint. This is it's also similar to both the models, but the only thing which is added here, only feature or step which is added here is distillation. But this looks like really good and realistic. So why there was a need of Sana Sprint is so there are like 40 to 20 steps per images in each step to generate an image. So each step is equals to one full neural network. So they thought of how do we collapse this 20 steps or 14 steps into one step. So that's what it's there in Sana Sprint. So if you will see here, these are the flux step, Sana sprint step, and there it takes four steps, 20 step, whatever it is. And if you'll see here, all the Sana models, the VAE is same because the encoder decoder always remains same, the train data always remains same. There is no need to change it. So you'll find it 0.212 seconds, 0.12 seconds. Only the transformer here is changing. So all speed comes from the transformer. Mm, okay. And okay, now next year. So if you will see here, the OOM stands for out of memory. So the red line is out of memory. So the max memory is of 80 GB. Uh, it's of one of the best GPUs. So 80 GB is the limit. So Sana Sprint trains 32 x more samples per step in less memory than the flux model needs like for just one sample. So flux model, uh, whatever memory flux model takes for one sample, Sana trains uses that much for only for 32 x model. So that's all quite a good. Okay, so the core idea, you can see here, the core idea of the distillation is, I'll explain it in analogical way, plus this way is teacher and student. So the teacher has large model, but it's low, but it has high quality, and student has small model, it's fast and wants to match the teacher. So the student doesn't learn from data directly. The student learns by copying the teacher's behavior. So whatever the loss is the difference between the teacher's output and the student output. So in this pipeline, the if you'll see, X0 is the real image. DAC is frozen. This is the real image. It is frozen here. And uh, this is the noise added. And we get XT trig. So this is the random question noise added. And this term is noisy latent in trig flow format. So this is basically trig is trigonometry. It uses sine, cos, parametric stuff for noise scheduling. Next is there are three transforms. Now, why do we need this transform? I'll explain it later. But first, there are three transforms. After this, first is input timestamp transform. This is the formula. It converts the time steps from trig flow format to flow matching format. Now, if you'll see, only this model needs trig flow and but the actual other two models were using flow match. So in order to match this, these three formula acts as a bridge between all the models and this model, so that gap is removed. So these three models converts that trig into match flow. So anyways, second is input latent transform. So this is the formula, and it rescaled the noise latent to match the flow matching. So it is a standard deviation. The output transforms. This is the formula. It converts the student's output back to trig flow format for consistency loss computation. So yeah, then I said why we need this transforms. There is no need to train everything from scratch in this also. Then let's see this part. The input here is X and FM. So noisy latent in flow match format. The output here for the teacher, no, teacher is frozen, and the output we get here is dxdt. This is the velocity direction of the denoise, and it knows the right denoising direction at every time step. For the students, its student is trainable, so the input is same noise latent, and it gives the student predicts the clean image and JVP. JVP is basically vector product. It is needed for the consistent computational loss. Now this has two loss function: SCM loss and GAN loss. So SCM loss is self consistency. So student output, whatever the student, if we take any frame, any time step, and from anywhere, plus we take another time step from anywhere, so both the time step, the x0 should be same. So that's the thing, that's what SCM loss is. So difference between the two prediction. The JVP is change. It's how the student output changes with respect to timestamp, with respect to t. This is what makes the model step adaptive. So basically, self consistency is no matter what time step you start from, the predicted clean image should be same. For example, t 0.9, t 0.8 or T1 all should have the same predicted image, that is X0 should be same. So if this holds, then model can jump from any timestamp to any other timestamp in between, and it could get same X0. So there is no need to do 100 things. We can just do it in one step. Second is GAN loss function. Now in this, so XG and trig is the noise latent, and the student generate X0, which can be, if it is fake, it is labeled as fake. The real image is labeled as real, and there is a discriminator head, which is trainable. It's the real or fake. So how well we discriminate can tell. That's what can tell them apart. So teacher the teacher is frozen. It's also fed into the discriminator as a reference. So it provides what actual generation looks like signal. So GAN loss is on top of SCM. First two, so SCM, so this two. So first, SCM loss alone, it ensures the consistency, the correct contact, but can produce slightly blur output. It ensures consistency by the timestamp should be same. That's how it ensures. And in GAN loss, it ensures realism, sharp, photorealistic. It uses discriminator for single step to look if something it to make something look real. So in overview, it this forward pass training, it uses 5 steps. First is take the real image, then encode it with DCAC, then add a random noise, then transform it. This is all the transformer part. Then feed it to both the teacher and student. So this is the comparison between other models and Sana's print. In just one step, it gave very good generation into this. This is for the second image. In 2 steps, it gave really good image. So compared to other models, it is really good. Okay, so this was all about Sana and its image generation model. I think next session we will see the everything about video generation model. Then I also cover Kimi and a DeepSeek video generation model, then real-time streaming and how everything works. So yeah, okay guys, that's it. Have a good day.